Now let me turn things over to our presenter. Bob, the floor is yours.
Thank you, Chris. Hello, everyone, and thank you for joining. We are going to talk about the relevance of motion to many existing and emerging applications in industry, and specifically where performance matters and how to achieve it. We will talk about this in the context of the Internet of Moving Things, but you will see that many of these are relatively familiar applications, but with precision sensors and smart integration, there are significant opportunities to add value and drive growth. We'll start here by establishing the context with the applications and highlighting the challenges. Then we will discuss solution paths, starting with the core technology and how it works. We mentioned the IoMT, or Internet of Moving Things, but the broader context is autonomy. What used to be simple or fixed becomes increasingly intelligent and autonomous. So measurement becomes control and then leads to more automation. To a large extent, what is driving this are sensors. And sensors are becoming increasingly complex, higher performing, fused, more and more intelligent and connected as well. And ultimately, we see what were discrete elements or operations merging together. So we have a broadening base of equipment or machinery or nodes in general, which become increasingly relevant to us because of rich sensor content, making them contextually aware. Many, and I would say nearly all of these nodes, involve some type of motion or the necessity of lack of motion, which becomes a critical operation as well. While there may be some infinite number of applications, this discussion is far less concerned with the commodity use cases and is instead focused on high-value applications, where if the designs are done correctly, there will be significant market growth as well for years to come. These high-value opportunities are typically distinguished by some critical need at the system level. For instance, a very high level of precision or accuracy, or a drive to increase efficiency of resources, and certainly in many cases a need for higher levels of safety. So in each case, we've pointed out some typical applications and needs. For instance, looking at a smart farm, there's a very important drive to improve the operational efficiency of the farming operation, which typically means improving resource optimization, reducing the amount of seed, fertilizer, and water that's used in any given cycle. Certainly in these cases, we need to be sensing multiple types of parameters. Their specific location is incredibly important, and some amount of historical databasing and referencing comes into play as well. Similarly, in a smart factory, a need for predictive maintenance to reduce downtime, so a drive for better and better vibration sensing, for instance. Applications where accuracy is becoming more important, certainly surgical navigation, construction, for instance, road paving equipment, and various types of autonomous vehicles. All of these are looking for very high levels of precision, which means highly stable sensors. And not only that, sensors that can maintain that stability under all conditions. And certainly most of these applications are going to be more and more concerned about safety. These are typically large pieces of equipment or very high value assets or vehicles operating in the air. So designing for reliability, immunity to environmental influences, and designing in some level of fail-safe modes is likely to become more and more important. This translates that view to specifically look at the relevance of motion for a set of the targeted applications, or more specifically, what type of motion may be important. So you can see that geolocation, or the idea of knowing where on Earth we are, is prevalent. The level of accuracy can vary from meters for some use cases, depending on the time variable, to centimeters for equipment on the smart farm, or even to millimeters for precision surgical instruments. But beyond geolocation, there are a number of other motion elements that become important. I'll try to point out a few of those here. Looking at the smart farm, where much of the equipment today is GPS guided, there's actually a drive to get better accuracy than the GPS itself provides. And for those cases, we would use motion sensors to detect the roll and pitch of the equipment and use that information to stabilize the GPS antenna and improve its accuracy. In the case of UAVs and drones, many opportunities for motion to add value beyond geolocation. One of those would be in the precise pointing of the payload, wherever that may be. Looking down the list, virtual reality becoming more and more entertaining and precise at the same time through the use of fusing multiple sensor types and the use of the inertial sensors to very accurately point those as part of that operation. Multiple autonomous vehicles, land, air, and other, and opportunities for not just, again, geolocation, but vehicle dynamics, dead reckoning, and accurate pointing of the multiple suite of sensors. Another one would be in the case of antennas or cameras installed on buildings for communication or for security, beyond just the pointing application, perhaps using the motion sensors as part of the initial calibration and installation. Some of these applications are pictured here. As you can see, they are quite varied, but they have in common some means to detect, measure, analyze, and control motion. Normally, this will be with a combination of sensors, as shown in the block diagram, likely merging inertial measurement with other sensors like GPS. These get intelligently merged at the system level to produce guidance and control outputs. Many of these applications have difficult operational scenarios where no single sensor can be sufficiently precise under all conditions. The system designer needs intimate knowledge of the intended operating states and needs to identify sensors which complement each other well for precision across all states. For inertial sensors, which do not require any external infrastructure and do not have natural enemies such as urban canyons or bad weather blockage, the important parameters are noted here. For instance, very stable outputs, ultra low noise, and immunity to things like vibration. If we bring together all that we've discussed so far, our system looks something like this. We identify here 7 main elements to the node, 2 different types of sensors, context and motion, 2 levels of processing, sensor fusion and application level, connectivity, whether it be to adjacent nodes or to cloud-based processing, and the increasingly important security. A core message here is, despite all of these elements being important, is that the quality of the sensor elements is fundamentally important to the accuracy and to the usefulness of extractable information of the node, and ultimately to the value of the system. The rest of today's discussion is going to focus just on the last 3 listed here: position sensors, sensor fusion, and system-level considerations. This next section is going to focus on motion sensors, how they work, what are the challenges, how different types of sensors compare in terms of accuracy, and integration options. First, it is important to distinguish simple versus complex motion. Certainly there are applications where something on the order of up, down, left, right might be good enough accuracy. It may also be acceptable in those cases to draw a tight box around the allowed operational conditions, or at least be very forgiving of accuracy errors. Those use cases are not what this discussion is targeting. Instead, the reality of the applications we have highlighted is a much more complex scenario. So in the case of industrial applications, we will be looking for accuracy better than 1 degree, down in the 10th of a degree accuracy levels or better. Most likely, in the case where we have multiple sensors in this application, we will also be more heavily reliant on the inertial sensors because of the states of operation, perhaps GPS denied or others. So what that means is the inertial sensors will be more heavily weighted in the sensor fusion. It's also quite likely we will be operating under extremely complex or unpredictable conditions, and we need these sensors to be able to still reliably operate in those conditions. So ultimately, the sensor accuracy in many of these cases becomes the single most important mission critical item. Simple versus complex can be addressed with two very different grades of sensors. Low precision versus high precision, or consumer versus industrial. A high precision sensor, as I noted, will most likely be the primary sensor in the overall solution, more heavily relied on, and certainly capable of providing precision information even under these difficult conditions. What that means is the sensor needs to provide extremely low noise, very stable operation, even under the conditions of, say, vibration extremes or temperature. And with that, we would be able to achieve accuracy perhaps on the order of a 10th of a degree or even better. A low precision sensor, on the other hand, is most likely going to be simply a backup sensor to something else that is the primary accurate device in the application. What this means is it'll be generally fairly low, have generally low weighting, and would only be looked to under very narrow set of conditions. Many of these low precision sensors, in fact, tend to have quite low noise because of what they were originally designed for. However, they also tend to have fairly poor stability or very high drift rates that become even more severe or problematic under conditions such as vibration, temperature, and shock. And what that means is when everything is summed together, all the error sources of these lower precision sensors, our accuracy level, probably best case, is in the few degree level, if not much worse. Before moving into a discussion on sensor operation and a designer's challenges in system integration, we highlight here some of the foremost challenges relevant to the motion sensors. One of these being the basic level of accuracy that we can achieve, particularly in primary sensor. For instance, in a dead reckoning situation where we may be using GPS for much of the guidance, but we have a GPS blockage or denial. And we want to still achieve centimeter level accuracy. We also want to ensure ourselves that we are choosing sensors that can maintain that accuracy under these difficult conditions, which can include, as I've already mentioned, vibration, temperature, but perhaps wind and other disturbances. And certainly we need to be cognizant of choosing devices that can provide a very high level of reliability and quality, and perhaps are not prone to things such as lifetime drift, which may not be as obvious from looking at a data sheet. So there are many sensor choices available to the designer, but many fewer choices that provide high accuracy under all conditions with reliability. To meet these challenges, let's look at the steps or integration required between the basic core sensors and achieving reliable information from them at the system level. So this diagram is intended to show kind of the migration or the integration required between those core sensors and getting the application level information out at the right hand side here. There's a couple key processes or steps that we need to go through to achieve that. The first being enhancing or optimizing the performance of the sensors themselves. This is typically done through additional test and calibration, perhaps some first-level sensor fusion. One of the key inputs to this is a very high level of understanding of the motion dynamics, the general motion dynamics, and also a very good understanding of the core sensors themselves to help optimize the calibration, to focus it on those error terms that can be most problematic to not only optimize the performance but the cost. The second half of this is typically more at the system level, involving a higher level of sensor fusion and application level processing. Obviously, this requires a deep understanding of the application to know the potential conditions, operational scenarios, and thus map the sensors that are being used in the system to the most reliable and optimal configuration. So we'll discuss both steps as we move forward here, the sensor optimization and the system level integration, but we will go into a bit more depth on the sensor. Here we are going to quickly step back for those that are less familiar with inertial sensors and point out some characteristics that are important to understand to the broader IMU discussion. A MEMS accelerometer is much like the familiar mass spring system. So we're looking at F equals MA, where we know the mass, we can determine force from a spring constant and a displacement that we are able to detect with a differential capacitance approach, where we basically have two sets of interdigitated beams, one fixed and one movable. And when the device is under acceleration, we are then able to detect this capacitance change. An important thing to note here is that MEMS accelerometers are sensitive to both dynamic and static acceleration. What that means is they can detect gravity as well. So keep that in mind, and we'll come back to that point in a moment. Gyroscopes exist to measure angular rate. A common principle used to do this is the detection of the Coriolis force. So if we have a mass in motion on a platform, and that platform is under rotation, in order for that mass to maintain a straight line in the presence of that rotation, it would have to exert a force on itself in the opposite direction of the rotation. And that force is called the Coriolis force. And it is the job of the gyroscope to detect that Coriolis force with a great level of precision. The actual sensing element of the gyroscope looks very similar, in fact, to the accelerometer beam shown on the previous slide. So the reason for pointing that out is that means that the gyroscopes can also be sensitive to what we call G effect, some sort of G influence on its primary measurement of angular rate. So that's an important point. Another one being what I highlighted a moment ago is that the accelerometers, because they detect both static and dynamic acceleration, they cannot distinguish one type from the other, cannot distinguish acceleration from tilt or gravity. Thus the need for an IMU. So pictured here is a typical IMU within a larger INS system. I'll describe some of the key things here. The light blue shading is highlighting what would typically be integrated in an IMU. And as you can see, that involves multiple sensing types across multiple axes: angular rate, linear acceleration, magnetometer sensing as well in some cases, and barometer. Beyond that is a highly optimized signal chain of sensor conditioning and sensor processing. Implied in that is a very high level of calibration, which then drives the compensation of the sensor outputs based on the state of the device, for instance, its temperature. And also involved there is a high level of improvement on the alignment of the sensors themselves. So there is some first-order sensor fusion that goes on there. So typically this is anywhere from 4 to what we call 10 degrees of freedom. And on the back half of this is additional system-level processing, where we merge these inertial sensors with other navigation or stabilization sensors, such as noted there, GPS, radar, LiDAR, and other. A key input to that system-level processing is, of course, a high level of understanding of the specifics of the system, what the boundary conditions are, what operational scenarios we'll be working under. And a very core element here, of course, is the common filter. The job of the common filter is to take as inputs all of these sensors, but also have a very good understanding of which sensors work well under which conditions, and to have that system-level information about boundary conditions to thus determine the weighting for the sensors and to manage the handoff from one sensor to the other. All of this then is combined to provide, depending on the application, heading, orientation, attitude, positioning, so on. And in some cases, using these sensors as part of a servo loop for a stabilization of whatever the platform or the payload is. You are probably not surprised to hear that there is a substantial difference between the IMU in your cell phone and the one needed to fulfill the application challenges we've described here today. In fact, most sensors, whether they're low-end or high-end, typically today have fairly low noise. This is because even in low-grade sensors, they're designed for fairly short-term operation, and low noise is important in that case. So that is fairly typical. What is less typical is to have a high degree of stability amongst the sensors. So our choice of sensors becomes much more restrictive when we're looking at things like in-run stability. When we look at the specifics of any given application, we are going to be concerned about many other specifications as noted here, things like vibration or G-effect and alignment. Basically, in many cases, these are not specified in low-end sensors, and thus it would become impossible to determine the actual performance without an understanding of those error terms. So the best inertial sensors will for sure specify all of these, and more importantly, they will, during their design phase, will go to great lengths to make sure that all of these specifications are well balanced, so no one term becomes the dominant error source. So to describe this table just a little bit is just to show in summary, not all of the specifications, but some of the more important ones for gyroscopes and accelerometers. And as noted, noise being important, you notice a very low level of noise on both devices here. Also, looking at things like repeatability, which many specifications will not cover. They are covered here and showing a very high degree of repeatability or very low drift over the long term and all conditions. What's also noted at the bottom of the table are some of the specifications which, as discussed earlier, can become the more dominant error terms. So they're pointed out here, and again at a very accurate level. And you can see in comparison the third column showing how these somewhat typical industrial specifications would compare to a typical consumer level device. And you can see a very wide range of performance difference. So in summary, I would say the ante for an acceptable solution to a design could be things such as wide dynamic range and maybe low noise. But the decision factor may actually turn out to be something like in-run stability. However, the true enabler will most likely be specifications such as linear G, alignment, and temperature drift, and others. And finally, what will be further distinguishing factors at the system level will be things like bandwidth, vibration rectification, and perhaps repeatability. Here's an example to better demonstrate the point that certain factors like linear G and alignment are the true enablers. Actually, they become the dominant error sources if not designed right, and can be the downfall of a system design. So the table on the upper right discusses the situation of stabilization accuracy as shown on the left, where we would be using inertial sensors for stabilizing a payload on a vehicle. And we want to achieve accuracy, point-in accuracy, better than a degree. We'll be concerned about the amount of jitter in the servo loop, and we'll thus look at least at these three specifications: noise density, linear G, cross-axis. So we've shown the specifications of an industrial sensor here, and for a given set of assumptions, we've shown the impact on the error budget of that specification. And we've done that for both an industrial device and a typical consumer device, noting that in fact the typical consumer device does not actually specify those terms in red, so we're actually being probably fairly forgiving here for that device. But you can see in an industrial specified device, these specifications are fairly well balanced, so none overly dominates the others, or we don't disturb the noise performance too much with from linear G or cross-axis. In the case of the consumer device, you can see that is typically not the case, where a term like cross-axis, which is usually not very accurate, becomes the dominant error source and ends up with on the order of a 20x difference between these two devices. Another use case, of course, being navigation, where we may look at percentage of distance traveled, the error as a percentage of distance traveled. A very high-end military device may give us a 1/10 of a percent accuracy, whereas a typical consumer device is going to be off substantially from that. The interesting thing about the newest industrial devices that are available today is that they tend to be far, far less expensive than military-grade devices, but fairly close to them in terms of accuracy. And what that accuracy improvement buys us at the system level is a far less complex sensor fusion processing job at the back-end processing. Before moving on to some application examples, it's appropriate to make some comments on sensor fusion, what it is and what it is not. So certainly one thing sensor fusion can do for us is, in the case where a given sensor has some potential drift characteristics, if we have other sensors or other devices or other information in the system which can accurately resolve these conditions, and we do understand already how the sensor itself drifts under those conditions, we can use all that information to do some correction on the sensor itself. And certainly the sensor fusion would be used to hand off from sensor to sensor based on the weighting determined and the application, the operational scenarios, and our understanding of which sensor maps best to any given state. So two key roles. But certainly sensor fusion cannot fix what are poor quality sensors to begin with. And I'll try to demonstrate that point with a conceptual example here. Two cases. consumer dead reckoning. Now, typically, the sensors used in a device like this, for instance, a mobile phone, would be used out of convenience. What sensors are already there, and how can we use them for a particular app to, in this case, give us some navigation aid? So in that case, GPS will be the predominant sensor relied on for the navigation. And because the other sensors were not necessarily chosen to give extremely good coverage under a GPS blockage, we end up with a large amount of uncertainty. So the portions of the pie here are supposed to conceptually show the amount of reliable coverage from a given sensor. And because of that particular use case, there's a large amount of uncertainty. On the other hand, in an industrial application, normally we'll be choosing sensors specifically for the job at hand. And we very likely would be looking at much higher grade inertial sensors to provide a more reliable level of coverage, particularly when we have a GPS blockage. So the other sensors, still quite reliable in certain instances, but perhaps less heavily weighted. Now the weighting here might get flipped, but the point is we have a much more full coverage, a much lower level of uncertainty across the full state. Now algorithms exist around all this to help tie all this together and do the sensor fusion. The key thing is the algorithms themselves don't fill that leftover uncertainty gap. So the quality of the sensor becomes extremely critical to the overall accuracy. So next we have 3 application examples to discuss why motion matters, starting with unmanned vehicles. So here we're just pointing out a few different use cases in a drone or a UAV for the use of motion sensing. Could be for vehicle dynamics, for basic navigation, or as noted before, pointing of the payload. In all 3 cases, we're most likely looking for very low drift, low noise sensors, multiple sensing types and multiple sensing axes. And because of the dynamics of the vehicle, the conditions it operates under, we want these sensors to be very good at rejecting vibration influence. On the other hand, another use case would be health and usage monitoring, where in this case we don't necessarily want to reject vibration, but we want to very accurately sense it. And in that case, we would look to a very different type of accelerometer, for instance, that has not only low noise, but a wide dynamic range and wide bandwidth. Wrapped around all this are some of the things we've noted: signal conditioning, the system-level sensor fusion, high reliability, and in some cases, we may be looking for devices which have a path or an option for DO-178, DO-254 avionics certifications, given the high reliability environment that they operate in. Coming back to Earth and looking at perhaps one of the most difficult and important applications, first responder tracking. So here we've partitioned the system or the operational scenario into 4 stages: arrival at the scene, deployment of the first responders, the operation inside the building, and the rescue operation. And we've noted the particular sensors that might be used, first as the primary sensor and then as auxiliary or backup, and approximately how much time they need to operate over. So one thing to note here is the significance of inertial sensing in all stages, particularly in the GPS denied inside the building and rescue phase. So in this case, we would be very reliant on extremely low drift inertial sensors, but we're also looking for some very high quality additional sensors in sensor fusion, since prior to relying on the inertial sensor, we want to have a very good understanding of our absolute location, and we may use other sensors such as ranging to help determine that. If we think of this as asset tracking, and more specifically high value asset tracking, we can broaden the use case beyond first responder and we may then analyze the system designs in a similar way, identifying appropriate sensors by phases. Finally, we take a look around the smart farm. This is a highly complex system of systems, multiple types of equipment, multiple resources that we are trying to manage, not just manage, but optimize: water, seed, fertilizer, pesticide, sensors or equipment on the ground, in the air, in the ground, other variables to consider such as weather, historical data, and also very heavy equipment being operated and a high concern on safety as well. So this is certainly an area that is enabled by a very highly accurate position sensing capability, but overall it's a very sensor-rich, many other sensors involved to accurately do this job, and certainly a high level of connectivity as well. To enable any of these opportunities, sensor choice does matter. Specifically, we've been looking at high-value applications, many of them emerging, where the level of market acceptance and the rate of growth is certainly going to be somewhat risked by the ability to provide high level of performance, safety, reliability, and so on. The challenge is doing that without compromising some of the other system-level goals. Basically, in many cases, will come down to a couple choices. There's certainly a attraction on the level of system designers to look at the cost attractiveness of consumer-grade MEMS. Obviously, there's compromised performance to be considered there, and because of that, there typically is going to be a fair amount of added costs from additional tests, more calibration, and probably just yield loss. On top of that, there will be a need, because of the complex environments that these sensors are trying to be used in, for a additional packaging at the system level to dampen vibration or to thermally isolate the devices. In many cases, sensor fusion would be relied on for some sort of fixing or attempted fixing of the lower quality sensors, and there's obviously some concern of the usefulness of that. There's many other concerns: obsolescence, reliability, packaging level concerns about MEMS devices that need to be considered. On the other hand, there are the good news: there are industrial grade devices that not only provide superior performance, but they are ruggedized. They're basically ready out of the box to perform the functions that we've described as being needed here. And this can be done at the system level without having to compromise our size, weight, power, and cost goals. So I welcome you to investigate, after this call, some of the solutions which Analog Devices has specifically engineered to mobilize the IoMT. I've highlighted some of them here, from single, dual, triple axis gyroscopes and accelerometers to multiple degrees of freedom IMUs, and to some more specific functionality built around these sensors, such as tilt sensors or vibration monitors. And as well, an important capability in ultra-low power acceleration sensing for always-on sensing. Perhaps you may already be familiar with the solutions available today and their characteristics noted on the left, but I also want to point ahead to advances over the next several months. Our highest performance IMU line, which today already offers best performance for price, will be enhanced by 5x or more in performance. And our compact performance line, which emphasizes performance density and is today the market leader, will be previewing significant gains on all fronts: performance, size, and cost efficiency. Finally, I hope the discussion today has painted a picture for you of both compelling designer-level challenges and exciting market growth opportunities in the world of autonomous machines. We have emphasized the importance of the quality of the sensors at the core of these IoMT nodes because extracting precise information on context and motion from the world around us is not only the first step, but the most critical to enabling value at these nodes. I do thank you for listening and encourage you to look to these additional resources for more information. And I'll pass this back to Chris.
Thank you, Bob. Now let's jump right into Q&A. Here's our first question. Is it possible to use less integrated sensors, such as an accelerometer only, or is a full IMU really necessary?
Okay. Yeah, good question, and a fairly typical one when looking at these type of applications. And the answer is certainly highly dependent on the application. And while it's certainly possible to attempt some of this with a single sensor, typically that becomes quite difficult. One of the reasons being, as I pointed out, that no one sensor does a fully accurate job of sensing its environment under all conditions. And as noted, an accelerometer not being able to distinguish between gravity and acceleration, or tilt and acceleration, is thus not able to give a highly precise level of positioning under some of the complex environments we talked about. And that's where we need to typically merge in a gyroscope, if not other sensors, to get a more complete view across all conditions of what's happening.
Okay, next question. Some consumer-level sensors are pretty low noise. Why are these not good enough for the industrial applications that were discussed?
Okay, great question. Yeah, as pointed out, most sensors today do have I would say, a pretty good level of noise. Certainly industrial sensors and the highest end military sensors can be a fair amount lower noise than the consumer devices, but the consumer devices are not bad. The issue really, and the reason they're not, is they're typically designed for very short-term sensing, and thus the low noise is quite important for that. But the issue is, can we achieve that low noise sensing even under, again, fairly difficult conditions? So for instance, one spoiler of the noise spec is the alignment of the sensors. Most consumer grade sensors have a relatively poor level of alignment, XYZ, even though they may be integrated on a single piece of silicon. That misalignment probably is on the order of 2% typically, whereas to maintain a very low noise under an actual application level design, we need noise on the order of 20 times better than that. And that can typically is only achieved through calibration. So what we really need to look at are all the error sources that can affect the noise. And if those aren't as equally well done or specified, then the noise is somewhat irrelevant.
Okay, next question. Which applications seem to be most significant right now for these industrial grade sensors, and why?
Great. Well, if I were to put it in one bucket, we see many of these falling in the autonomous machine area. And certainly that covers land, air, sea, other types of vehicles. But the drive for more and more autonomy. And of course that's relevant to the smart farm, the smart factory, even a smart missile, right? But I think what's more interesting are the newer applications that we see being enabled by this increase in sensor accuracy and sensor integration and enabling, opening up new ideas. So while there may be some prevalent ones today, what's exciting are the newer ones that are becoming available to us with these sensors.
Well, that concludes our presentation. On behalf of Electronic Design, I'd like to thank Analog Devices and Arrow for sponsoring this event, and of course all of you for joining. Have a great day.